Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying applications of first-order equations, specifically springs, but undamped springs. In the previous lecture, we saw that there were second-order differential equations that could sometimes be reframed as first-order differential equations. For example, when the force, F, doesn't actually depend on y, only on t, y prime, and y double prime, or time, velocity, and acceleration. Then we could reframe this second-order differential equation about y as a first-order differential equation about its velocity v. Now similarly, a second-order differential equation can again be reframed as a first-order equation when there's no dependence on t. This is called an autonomous equation. It represents a situation where starting the system at time t equals 0 or starting the same system at time t equals 5 would fundamentally produce the same situation. Okay, it can depend on y, y prime, and y double prime, but the time at which you start things moving doesn't really cause any difference to the behavior. This is referred to as autonomous. So suppose, for example, that the acceleration is some function of the position and the velocity. Well then, if I let v be dy dt as we've done before, by the chain rule, okay, y double prime is v prime, that's dv dt. But by the chain rule, that's dv dy dy dt. Therefore, it's dv dy times v. This is something we saw in the previous video. We can replace the acceleration with dv dy times v. So instead of y double prime being a function of y and y prime, if I replace y double prime with v dv dy, there's now only v and its derivative y. There is no t in consideration at all. So specifically, we now have a second-order differential equation of the form y double prime plus some function of y and y prime times y prime plus some function just of y equals 0. Okay, we replace y double prime with dv dy times v, and we replace y prime with v as before, and we end up with this. Okay, so we have replaced y double prime with this, and every time we see a y prime, we replace it with a v here and here. So now imagine y is the independent variable. Your height is independent, but your velocity depends on it. This is now a first-order differential equation. We have v times v prime plus some function times v plus some other function equals 0. Now in the original equation, if p of some value is equal to 0, okay, so this one here, if there's some value of y for which p of y is 0, then setting y to be constant will be a solution. Okay, if p of y is 0, when y is a constant, then its derivative and its second derivative are both zeros as well. So there might be some value of y being constant that solves this. That's called an equilibrium of the equation, a constant value of y for which nothing really happens. We can work then with either this differential equation where y, y prime, and y double prime are all functions of t, or this one, where v is just a function of y. But remember, they're the same differential equation. Using previous terminology, if the acceleration, in other words y double prime, doesn't actually depend on y prime, the equation is said to be undamped. There is not a damping force proportional to the velocity or velocity squared or something like that. So suppose the function q of y and y prime is constantly 0. So in this top equation, this term vanishes. I just get y double prime, which is proportional to some force, and here it only depends on y, but no longer any mix of y prime in there. That's called an undamped equation. So we're going to consider solutions to this undamped equation. Forces which act on a spring are described by something known as Hooke's law. If we have an object of mass m and it's attached to the end of a spring, there will be an equilibrium position, some position that is constant where the differential equation is satisfied. Now y is going to represent how far from equilibrium we are. Hooke's law specifies that the force acting is directly proportional to y and in the opposite direction. So the force, or mass times acceleration, is proportional to the displacement y. By specifying that k is positive, I can clarify that it's in the opposite direction by saying negative k here. K is called the spring constant. It essentially dictates how springy the spring is. Now this equation can be converted into the undamped equation. My prime plus ky is 0. Notice there is no intermediate term that involves y prime, so this is undamped. This can then be reinterpreted as my prime, which is v dv dy, plus ky equals 0. So here's the undamped spring equation coming from Hooke's law. We can integrate this straight away. Okay, mv squared over 2 is equal to negative ky squared over 2 plus a constant. We've simply moved the ky over to the other side. Now we have a separable equation, mv dv equals negative ky dy. Integrate both sides, we get right there. Multiply both sides by 2, and of course 2 times the constant is just some different constant, so we don't really need to write 2c. We just end up with mv squared is minus ky squared plus c. Our initial conditions we're going to represent as y of 0 is y sub 0, and y prime of 0 is v0. Okay. We can then specify that c must be mv squared plus ky squared. At time 0, v sub 0 and y sub 0, and then we solve for what c has to be. It's just that right there. So m is the mass of the object and k is some spring constant. All right, so here is our solution. mv squared equals negative ky squared plus c. C is very explicitly presented in terms of the initial conditions, but for convenience, we're just going to leave it as c for now. Can we solve for this where y is a function of t rather than v as a function of y? All right, well, v we can solve as plus or minus the square root of c minus ky squared all over m. On certain intervals of time, the velocity will be positive or negative, okay? We're either moving up or down. Now let's presume that v is positive on some interval just so that we can proceed. Well, if v is positive, I don't need the plus or minus, I just call it plus, but v is dy dt. So dy dt is now positive the square root of all of this mess. So here's the differential equation we've arrived at. We're going to multiply both sides by a specific radical. Okay, we multiply both sides by radical k over c minus ky squared. So it shows up on the left, and on the right, that denominator of c minus ky squared cancels out what we had in the numerator. Okay, but we do introduce this constant k into the numerator on the right. Now, however, we can integrate both sides. Integrating the right is quite straightforward. I integrate it against dt, and I just get that constant times t, plus some constant of integration. And in these spring problems, the constant of integration introduced here is typically represented with the Greek letter phi, but this is just our constant of integration. Integrating this against dy, it's an arcsign. And specifically, it's the arcsign of root k over c times y. So now we have an arcsign of something involving y, and on the right, we have something involving t. Okay, we're going to replace some things with other letters just for convenience. I'm going to call capital R the square root of c over k, and I'm going to let omega sub 0 be the square root of k over m. So this is just the typical way to do it, but notice I let r be the reciprocal of this. So inside this parenthesis, I now have y over r. This was exactly omega naught, so we get omega naught t plus the constant phi. But now I can take a sine of both sides and multiply that r across. So what's the solution to our spring equation? Not terribly surprisingly, it is some constant times the sine of a constant times t plus another constant. Fundamentally, how do springs behave when they are undamped? Like sine functions. Altogether, where are we now? If a mass is placed on a spring and we subject it to Hooke's law, the displacement is given by a nice, straightforward sine function, but there's a bunch of constants in here that we should discuss. What are the various constants that show up? Let's take a look at r. It was defined as the square root of c over k. Now k is a spring constant, but also notice in this solution, r is exactly the amplitude of my solution, so it tells me the maximum and minimum displacement. Also, capital C, which appears in r, depended on our initial conditions, our initial velocity, our initial position, and our mass, and the spring constant. This makes sense. Okay, if I start with some velocity or I start at a great big height, that will change the amplitude of the oscillation. Also, omega naught is the square root of k over m. But in terms of the sine function, it determines the frequency of oscillation. The spring constant makes a difference. Okay, if our spring is very springy or not very springy, it will oscillate faster or slower. But the mass also makes a difference. Okay, as the mass gets very large, omega naught tends to 0. Okay, but 2 pi over omega naught is the period. So as the mass gets very big, the period actually gets very short. And finally, phi just represents a phase shift. It's derived from the initial conditions because, for example, I might start the spring at a certain displacement, but with a given velocity will kind of affect. I may not have started at the minimum or maximum displacement because it's got this initial velocity thrown into it. So phi helps account for that. I can begin at an arbitrary position within my sine curve.